Welcome back, everyone. In this video we're going to be covering the second page. That's the fill-in-the-blank stuff of the final exam from fall semester 2014 here in Math 234. Alright, so let's get to it. Problem number 5. Evaluate the limit if it exists. Write DNE if the limit does not exist. So something like this looks like we have the limit. X is going to 1, y is going to 2. Alright, so how do we solve these limit types of problems? Well, the first thing that we always try, right, is what happens if we just plug in 1 everywhere I see an x and 2 everywhere I see a y. So if I plug 1 everywhere I see an x, I'm going to have 4 on top, and 2 everywhere I see a y, I'm going to have minus 4. And then in the denominator, I'm going to have, let's see, 1 everywhere I see an x, that's going to be 2, minus, when I plug in 2 for y, I'm going to have 2. So this is going to be a 0 over 0 situation. So, I mean, it'd be nice if it was a real number, but sadly not this case. Okay, so the next step, really step 1, I see if there's any way I can use algebra to make things cancel. So that's like using factoring, or maybe getting a common denominator, or multiplying by a conjugate, things like this. So looking at this, I do see, at least on top, it looks like a difference of squares sort of deal, right? This seems like a perfect square, this seems like a perfect square. So I'm actually going to try to factor this. Alright, and I'm running out of room, so I'm going to come down here a little bit. So if I try to factor this, I think it should be like 2x minus y and 2x plus y. But let's go ahead and FOIL this out and make sure, right? So if I did the firsts, I would get 4x squared. If I did the inners, I would do, let's see, negative 2xy. If I did the outers, I would do plus 2xy. And if I did the lasts, I would get negative y squared. So you can see the inners and the outers perfectly cancel out. And I get 4x squared minus y squared. And that's exactly what I have up here. So yes, this is how I can factor that. Now in the denominator, I have 2x minus y. So actually we can see, this perfectly cancel out, right? I can go ahead and cancel it out, and now there's no problem plugging in a 1 everywhere I see an x and a 2 everywhere I see a y. So if I plug in 1 everywhere I see an x, I'm going to have 2 times 1. If I plug in 2 everywhere I see a y, I'm going to have plus 2. So altogether, I believe that my answer is 4. Alright, problem number 6. Evaluate the limit if it exists. Write DNE if it does not exist. Okay, so limit as as x goes to 0 and y goes to 0. So same thing as before. Let's go ahead and plug in 0 for x, 0 for y. This one you can probably see even, let's see, I'm going to have 0 minus 0 on bottom. So altogether, this is 0 over 0. So again, maybe the first thing we do is we say, okay, can we use some algebra to try to get things to cancel out? But unfortunately, right, that numerator right here, that's not going to factor. There's not a good way to factor this. There's no way that we can really cancel things out in this case. There's no square roots, so multiplying by a conjugate doesn't really make sense. There's already has one common denominator, so it doesn't really make sense to try to get a common denominator. It already has one. So I say, okay, well, what's next? Well, I go to step 2, right? So step 2 is trying to use this two-path test to show maybe that the limit doesn't exist. So if I was to use the two-path test, maybe let's first think about if y equals 0 and x goes to 0. So if y equals 0 and x goes to 0, well, if y's are equal to 0, I'm going to imagine that these are just gone here, right? So this is like adding 0. Now, as x goes to 0, well, actually, there's quite a bit of cancellation here as well, right? Because this would be x squared over x squared, so that would perfectly cancel out, and this limit would go to 2. Okay, so along this path, along y equals 0 and x is tending towards 0, the limit is equal to 2. How about with x equals 0 and y tends towards 0? So if x equals 0, well, all this bit's going to be gone. And now, actually, again, there's quite a bit of cancellation, right? So the y squareds perfectly cancel out. And so I have 1 divided by negative 1. So in that case, we're going to get negative 1. And so we can see, actually, from this two-path test, you know, if I go along these two different paths, we get different results. And therefore, we know that the limit cannot exist. So I'm going to write DNE. All right, problem number 7. Okay, we're given a derivative here, dr dt. Let's see, we're also given that at r of 1, we have some vector here, and we want r of t. Okay. So this is going to be like one of these chapter 13 things, right? We learned how to take derivatives and integrals of vector-valued functions. So let's go ahead and start with a proposal for r of t. So I'm going to integrate this. I think I'm going to get, and I'm going to switch notation here a little bit, because I like the with the brackets and stuff rather than the i's, j's, and k's. If you like the i's, j's, and k's, that's perfectly fine as well. So I'm going to integrate. So in the I component, I'm going to have t cubed plus t, so that's me integrating this first stuff. Now the second stuff I'm going to have t to the fourth plus t. And now thirdly, when I integrate -1, I'm going to have negative t. Now remember, when you integrate, you have a constant, so plus a c, but that constant, when you have a vector valued function, right, it is a constant vector. So there's really like a c1, a c2, and a c3. And that's what we want to solve for, right? So this is the beginning of r of t, but we need to know what that constant is, right, in order to get my final answer. So okay, let's make sure that when you plug in 1, we want to get out, let's see, in the first case we want to get out -3. So when I plug in 1, let's see, I would get 2 here. So if I want my end result to be -3, that means that C1 should be -5. So let's go ahead and double check. So if I plug in 1, I would get 2 minus 5. That would be -3. Perfect. Next up, let's see, there is no j component, right? So that's saying when you plug in 1, you want to get out 0 j's. So if I plugged in 1 into my second component, I would get 2. So in order to make sure that my end result is 0, let's go ahead and subtract 2. So again, this is going to be 2 minus 2, and that's going to be 0 j's. So that's why there's no j's there. And then finally, when you plug in 1 in your third component, you should get out 2k, right? So when I plug in 1, I'm going to get -1 here. So I'm going to add 3 to that in order to make sure that I get 2k. All right, so I think this should be the final result. Let's go ahead and write it down. So r of t is going to be equal to t cubed plus t minus 5. The second component is going to be t to the fourth plus t, and let's see, minus 2. And the third component is going to be -t plus 3. All right, I'm happy with that answer. Let's move on to problem number 8. So let's see, we have the integral here, and it doesn't list it, expresses the length of the curve r of t between the points 1, 1, 0 and 2, e, 0. Do not evaluate. All right, so I want to write down the integral that represents the length of the curve, or the arc length. Okay, and we have some parametrized function here. And so I need to remember, maybe off to the side here, that arc length is going to be given by the integral from a to b of the magnitude of the derivative of r. So let's go ahead and start calculating that out. So let's see, I'm going to have the integral, and I'll hold off on these for a second. I'm going to have the magnitude of the derivative. So let's take the derivative here. So of the first component, I'm going to get 2t. Of the second component, I'm just going to have e to the t. And of the third component, well, the derivative of sine is going to be cosine. Leave the inside alone. Then we multiply by the derivative of the inside. All right, so there's the derivative. Now let's go ahead and do the magnitude of this. So the magnitude, that's going to be 4t squared, plus e to the t squared. That's going to be the same thing as e to the 2t, plus, and let's see, if I was to square the second one, I could write it as pi squared cosine squared of pi t. So I square each thing here, add them all together, and that's what's inside of my integral. And now the only question maybe left that I have is, what should the bounds be? Right? Well, I know it has to travel between the points 1, 1, 0 and 2, e, 0, but the problem is that I'm taking an integral with respect to t, right? These are x, y's, and z's, right? And I need t stuff. All right, but we can solve for what should those t's be, right? So I'm going to take a look here, and I actually like maybe the second one the most. I'm going to look at the second one, and I'm going to compare over here and over here, right? So I have e to the t is equal to 1, right? And I want to know what t value makes that happen. So what value, when you raise e to that power, do you get out 1? Well, I think that means that t has to be 0. So t is equal to 0 in this case, right? Anything raised to the 0th power is 1. Okay, so if I start at t equals 0, I think that that would give us 1 in this coordinate. Let's go ahead and check the other coordinates, right? So if I was to plug in t equals 0 here, I would get out 1. That's good. If I was to plug in 0 here, I would get out sine of 0. That's 0. Good. So 0 seems to be my starting point. How about my ending point? Well, again, I'm going to look at e to the t is equal to e. Well, e is the same thing as e to the first, right? So this is saying, well, that t probably should be equal to 1. Let's go ahead and double check. Right, so if I was to go ahead and maybe look at my second one and I'd plug in t equals 1, I would get 1 plus 1, that would be 2. Good. And how about my third one? I would have sine of pi times 1, so that would be sine of pi. Sine of pi, is that equal to 0? Yes. So yes, from t equals 0 to t equals 1, those are the correct t values. So that should be my limit of integration. Okay, before I write this down and move on, you should be asking yourself, why did I choose the second component? How did I know that e to the t is maybe this good one to choose? And it's because e to the t has an inverse, or it passes the horizontal line test. Another way to see this is if you had started maybe with the first component here, right? And we were trying to solve, oh, how nice. If we were trying to solve maybe when does this equal 1, that would be okay, right? So 1 plus t squared, when does that equal 1? You would get t squared is equal to 0, so therefore t equals 0. And so you would get the same result as before. But in the second case, right, when you have 1 plus t squared, how does that equal 2? Well, in this case, you would have t squared is equal to 1 after you subtracted, and therefore t is equal to plus or minus 1. So, right, because this thing, 1 plus t squared, doesn't have an inverse, right? You can't uniquely solve for this, right? You don't know if it's 1 or if it's negative 1. So with this one right here, right, it has an inverse, so you can uniquely solve. There's only one point in which e to the t is equal to e, and that's at t equals 1. So again, kind of 1 was one of our options here, but we couldn't uniquely identify it. All right, so that's just a little piece of side information here. Let's go ahead and write down our final answer. So this is going to be the integral from 0 to 1 of the square root of 4t squared plus e to the 2t plus pi squared cosine squared of pi t, all of that under the square root, and then this is going to be dt. We're integrating with respect to t here. All right, so there is my final answer for problem number 8. Problem number 9. All right, blank is the equation of a tangent plane to the surface at the point 2, 0, negative 4. So an equation of a tangent plane. So I need to remember, what does an equation of a plane look like? An equation of a plane looks like a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Where x naught, y naught, z naught is a point that we want the plane to contain. So in this case, we have a point that's explicitly given to us, 2, 0, negative 4. And we have, let's see, a, b, and c. That would be the normal vector. So I have a surface here, and I'm wondering, how do I get the normal vector? And there are indeed multiple ways to get the normal vector. However, I'm going to use my favorite, which is using the gradient. So I'm going to bring this down, and I'm going to write it as maybe 0 is equal to x squared times y minus 1 minus 2y squared minus z. So right, I get a function of x's, y's, and z's is equal to a constant. So in this case, my constant is 0. And now I'm going to go ahead and find the gradient of this. So the gradient of this function here on the right-hand side. So if I take the derivative with respect to x, I'm going to get 2x. Let's see, and the y minus 1's along for the ride. If I take the derivative with respect to y, I'm going to get y squared, and let's see, minus 4y. And if I take the derivative with respect to z, I'm going to get negative 1. All right, so this vector is tangent to the surface at kind of every single point, x, y, z. We want it tangent at a particular point, right? Sorry, not tangent. We want it normal or perpendicular at a particular point, right? 2, 0, negative 4. So I'm going to plug in everywhere I see an x, I'm going to plug in a 2. Everywhere I see a y, I'm going to plug in a 0. Everywhere I see a z, I'm going to plug in a negative 4. So, okay, so 2 for an x, 0 for y, 2 for x, 0 for y, and there were no z's to plug in negative 4. Okay, fair enough. So the gradient vector at that particular point is negative 4, 4, negative 1. All right, so that should be my a value, my b value, and my c value. Now that we have those, we're ready to go ahead and write down our answer. So our answer again should be a times x minus x naught. So a was negative 4 times x minus x naught. So x naught is 2, the point that we want to hit, plus b was 4 times y minus y naught. So y naught is 0. plus c. C in this case was -1, so I'm just going to go ahead and do minus. And z minus z naught. So z naught in this case was -4, so minus a -4 is going to be the same thing as adding 4. That should be equal to 0. So that's the equation of a tangent plane to the surface. Z equals x squared times y minus 1 minus 2y squared at this particular point. All right, one more to go. We have a nice triple integral. We're integrating some function. It didn't tell us what the function is. And let's see, we were integrating z, y, x. Now we're integrating x, y, z. And the question is, okay, they've given us a few of these things, but they want to know what should a be and what should b be, right? All right, so I went ahead and I wrote down this problem down here just so that I don't have to keep jumping back and forth sort of deal. And let's go ahead and try to sketch this, right? In order to switch the limits of integration, we're definitely going to want a sketch here. So I'm going to go ahead and maybe draw, this is x, here's y, and here's z. I may need more, but we'll see. So x's, y's, and z's. And quite often when I go to sketch these things, right, I start outside in, right? I have to imagine that this is like a one-dimensional thing, right? Because this is after all the z's and the y's are gone and just x remains. And so it says that my picture lives between 0 and 2, x equals 0 and x equals 2. So this tells me that I'm drawing the picture in this region right here. Between x equals 0 and x equals 2, stuff's happening. Okay, now let's go up in dimensions, right? So up in dimensions, let's do y equals 0. So at y equals 0, that's actually back here. That's actually the green line that I went ahead and I drew anyway. And then I have y equals the square root of 4 minus x squared. So if I do y equals the square root of 4 minus x squared, and I want to know what does that look like. Well, first of all, I could do the point plotting method, right? Point plotting method would certainly work, or I can go ahead and rearrange this, and I can do y squared is equal to 4 minus x squared, and I get x squared plus y squared is equal to 4. So this is saying that it's part of a circle, right? And in fact, because it's the top square root, right, this means that it's the top half of the circle. And so now let's go ahead and verify here. For instance, if you were to plug in x equals 0, right? Now I've moved up dimensions. Before I was one-dimensional, now I'm two-dimensional, right? So I'm in kind of the xy plane and I'm drawing stuff. So if I want to draw the part of the circle that lives kind of between x equals 0 and x equals 2 in just the top half, right? So for instance, if I plugged in x equals 0, I would get out y equals 2. So that's going to be up here. Likewise, if I plugged in x equals 2, I would get, let's see, 4 minus 4. So I would get y equals the square root of 0, which is 0. So I'm going to have the top half of the circle, right, it would look like this, kind of in the xy plane. Again, kind of sometimes it's nice to look at the xy plane as, you know, actually just a good old two-dimensional thing. So I'm going to draw this picture, this same picture, here in just the regular old xy plane. So that's my green line there, and here is my, looks like a quarter of a circle. So this picture refers to this stuff right here. Okay, now finally my bounds for z will be from z equals 0 to z equals 3. So z equals 0 I already have, that's very nice. And so let's go ahead and draw z equals 3. So up here, so z equals 3 is a nice plane. It goes on forever, kind of in all directions. But it's just, remember, when we smash down, we need to get this region right here. So this is only going to be kind of maybe a quarter of a cylinder or so. It looks something like this. So that's what our three-dimensional region looks like. A quarter of a cylinder. So now let's go ahead and let's stare at, it wants to do x first, then y, then z. And it says already z is going to be from 0 to 3. That kind of makes sense. Okay, so if I wanted to do x first, so I'm traveling in the x direction, maybe I'll use purple here, so I'm kind of heading in this direction, the positive x direction. The first thing that I hit is going to be this flat plane right here. Now this is going to have the equation x equals 0. Okay, so that actually we already knew, right? So it told us we hit at x equals 0. Now how do we exit this region? Well, we're going to exit through this curvy bit. This curvy bit is going to be how we exit this region. And so remember, that comes from the equation, right? X squared plus y squared equals 4. but now I need an x value, so I need to solve this x equals. So if I go ahead and I try to solve this x equals, I'm going to have x squared is equal to 4 minus y squared, which is going to give me x is equal to plus or minus the square root of 4 minus y squared. And so I have to decide, right, should it be the positive square root or should it be the negative square root? But notice that this is to the, well, I'm going to say to the left, right? It has positive x values, right? It's to the left of this y-axis here. So we have positive x values. We're along the positive x-axis here. So therefore, right, we want this to be the plus, right? Because the square root will only ever spit out positives. So if you choose the negatives, you turn all those positives to negatives. And if you choose the plus one, you keep them positive. So I'm going to keep them positive because, again, we have positive x values here. So, okay, this is telling me that my upper limit here, in this case b, is supposed to be the square root of 4 minus y squared. Okay, next up, if you were to smash, right, so that there were no more x's in the world and all that was left were y's and z's. So something like this. If we were to take this region and smash, so all we had left over were y's and z's. Here's y, here's z. Again, z would go from 0 to 3. Y would go from 0 to 2, it looks like. Right? And I'd have this region right here kind of smashed into the yz plane. So in this case, it looks like my upper limit of integration for y should be 2. Right? Because next up, I'm integrating with respect to y, so I'm traveling in this y direction. I enter in through y equals 0. That's the straight up and down region right here. And I leave through y equals 2. Again, a nice straight up and down region, 2. So again, we already know 0, but now we know 2. So at a equals 2 and at b equals the square root of 4 minus y squared. Those are my answers for problem number 10. Alright, that's it for this video. Sorry, I know it's kind of a long one. I hope these explanations are helping you out though. I'll see you next time.